Hello and welcome to episode 0 of this series on Coxeter groups. In this video we'll be discussing the foundations of group theory, reflection groups and how they relate to tiling. So yeah, let's get straight into it. First of all, what is a group? Okay, well a group is a set which we'll call G for group. Okay, not G for Goran, unfortunately, but you know, it's a happy coincidence, I suppose. Okay, and this set is paired with a binary operation, which we will denote with a dot. Okay, and that just means that you can combine two elements of your set G in some way and get a third out. Basically, you can do addition. Okay, now that's not enough. Okay, a group like this with the binary operation has to obey some rules which we call axioms, and they are closure, associativity, identity, and inverse. Okay, those are the names of the four axioms. And what do they mean? Well, closure says that for all A and B in our group G, if you have A operate B, that stays in G. Basically, you don't get anything weird that comes out the other end. You don't get some crazy answer. It stays in the group. Okay. Associativity says that for all A, B, and C in G, if you have A operate B operate C with the brackets around A and B, then that is the same as A operate B operate C, but with the brackets around B and C. And that just means, you know, it looks confusing, but I'm sure you're familiar with it. If you take, for example, addition, like I mentioned before, you know, that is an associative operation because you got 2 plus 3 plus 5. You can do 2 plus 3 first, you get 5, and then add the 5, 10. Or you can do 3 plus 5 first for 8, and then add the 2, and you still get 10. Okay, it doesn't change the answer. And that's all associativity is. Third rule is the identity law. Okay, and that says that there is an element which we'll call E in our group. Okay, and such that for all A in G, A operate E equals A, and E operate A equals A. Basically it's a does-nothing element, okay? We need something that keeps everything sort of as it was, okay? And finally, inverse laws say that for all A in G, there is B in G such that A operate B equals the identity and B operate A equals the identity. Basically there's a way of going backwards, right? Okay, there's a way of sort of doing the opposite. Okay, so that's all nice and good, and you know, but it is kind of abstract. Okay, I think that to really understand groups and group theory, it's good to go over some examples. So let's do that. Okay, the first example I would like to cover is the integers. Okay, which is, let's swap to black again. Okay, which the integers we label with a fancy Z. Okay, I believe this Z comes from the German Zahlen, which means number. Okay, and we're going to pair that with addition. Okay, Now, I'm not going to write down all the axioms again and try to prove them all for this, okay, but let's talk through them, okay. What is an integer? It's a whole number. So for the closure axiom, okay, for the closure axiom, if you add two whole numbers, do you get a whole number? Well, yeah, I'm pretty sure that's right. Associativity, well, we did an example earlier, okay, and you can double check yourselves that works for all whole numbers. Is there an identity? Is there a does nothing element? Well, for addition, the does nothing element, and what do you add to something? What do you add to a number to leave it as it was? Well, you add 0. So that's your identity. And then inverses, well, that's just all the negatives, right? Because if you think about it, so suppose you are on +2, okay, and you want to get back to 0. And you might think, oh, just take away 2. But the problem with that is that you're not allowed to do that in the group, because the group only has one operation, addition, and so you have to be a little bit clever. And so instead of subtracting 2, you have to add -2. And as we know from primary school mathematics, when you add a negative number, that is equivalent to subtracting the positive version, okay, and so 2 add -2 is 0. Okay, so the integers under addition form a group. Wonderful, brilliant. Quick, not so much a tangent as just a little thing to note. If you do the integers with multiplication, okay, then that is not a group. That fails, okay, that fails to be a group, and it fails on the inverse law. Okay, all the other ones are absolutely fine. It's closed, you multiply two whole numbers, you get a whole number. You can multiply in any order. There's an identity, that's 1. But for inverses, if you are on, let's take +2 again, and you want to get back to the identity under multiplication, you have to either divide by 2. You can't do that because there's only multiplication. Or so instead you would multiply by 1/2, okay, 1/2, but you can't do that because 1/2 is not an integer, okay, 1/2 is a fraction, okay, so integers under multiplication do not form a group. Let's look at another example that actually is a group this time though, okay. And we're going to look at the cyclic group of mod 6. Okay, now what does that mean? Well, if you take the number line, okay, and so you've got, we'll put 0, 1, 2, 3, 4, 5, 6, 7, and so on that way, and we'll put in a couple of the negatives here. Okay, so you've got your number line, right? Okay, and this stretches off in both directions off to infinity, right? But what if I say, okay, well, I'm going to say that after 5, okay, or after 6 actually, I'm going to say after 6 we stop. Okay, when you go, whoa, you can't just stop numbers. Okay, and so I say, well, no, you're right, I can't. So what I'm going to do instead is I'm going to loop back round, okay, so that you have the numbers up to 6. And once you get to 6, instead of 7, okay, you loop round to 1. Okay, so 7 is equivalent to 1, right? And equally, 0 is equivalent to 6, -1 is equivalent to 5, and -2 is equivalent to 4, and so on. You could do this. You can do this for all integers, really. Okay, and what I'm actually going to do is I'm going to put a division after the 5 and before the 0. Okay, because adding 0 to a number is well, not a lot easier, but it's marginally easier than adding 6. Okay. So what you end up with is the numbers 0, 1, 2, 3, 4, and 5. Okay. And these are your set. Okay. And technically, that isn't actually what you end up with. What you end up with is equivalence classes mod 6. So we denote that with square brackets around all of these and a small 6 afterwards. I'm not sure how clear that is on the screen, but you get the idea. And all this means is that when you take a number and you divide it by 6, you ignore what the whole number answer is, and you're only interested in the remainder. So if we look at 13 divided by 6 is 2, don't care about that, and remainder 1. So 13 is equivalent to 1 mod 6, so it would be in this equivalence class. Okay, and if you do the maths on this with addition, okay, then this is a group. Nice. Okay, so we label this is actually called C6, okay, C for cyclic, because it cycles around. Okay, so C6 under addition is a group. Now, if you are familiar with imaginary numbers, then you might be familiar with the roots of unity. Okay, and I'll quickly explain what that is. So the roots of unity are basically, if you've got an equation like this, z to the 6 equals 1, then in the real numbers, okay, what we're used to working with, so 1, 2, 0, a half, pi, e, all of those, okay, all the real numbers, or everything on the number line, basically, okay, there are only 2 solutions to this, okay, positive 1 and negative 1. 1 to the power of 6 is 1, minus 1 to the power of 6 is 1 as well, all right? But in the complex numbers, there are actually 6 solutions, and that's actually the fundamental theorem of algebra, that in the complex numbers, every polynomial, okay, has its maximum degree of solutions. Okay, so z to the power of 6 equals 1, okay, has 6 solutions. I'm not going to list them all out because I can't remember them off the top of my head, and they're a bit confusing. But what I can do is I can plot them on an Argand diagram. Okay, so we put the real axis here, and the imaginary axis goes vertically. Okay, and we can plot all the complex solutions to z to the 6 equals 1 on here. So we've got 1. Okay, I believe it's a half plus root 3 over 2 I. I is this imaginary number where I squared equals minus 1, if you didn't know already. Okay, and I'm not going to write them all in, but what you end up with the roots of unity is you end up with a regular, if you join up the points, then you end up with a regular hexagon like that. Now, what's really cool is that if you multiply any 2 roots of unity together, you always get another root of unity. It never leaves. And what else have we seen regarding things that never leave? Groups. So the roots of unity form a group. And actually, the roots of unity, if I put, and let's do that in a different colour. Okay, if I do the roots, if I put 0, 1, 2, 3, 4, and 5, okay, then the roots of unity, each of these, okay, each of those points are isomorphic to C6. And what all that means is that they're not the same group, but they have the same structure. And what's really cool about that is that you can use maths from one to prove things in the other and do things in the other, and it makes it a lot easier. Because if you want to multiply two roots of unity together, okay, say the fourth and the second, right? You have to do complex multiplication, okay, and that takes a long time. However, if you convert that to, if you convert it to C6, okay, and so you end up with 2 and 4, well, 2 plus 4 is 6. 6 is equivalent to 0, okay, so the two roots of unity multiplied together get you the first, okay, or 1, okay. And I think that's really cool. Okay, you know, I love isomorphisms. You might have already seen my video, which I should hopefully be able to link up there or in the description, about isomorphisms, where I go into a little bit more detail. But yeah, I think they're great because they connect random bits of mathematics together, and you know, where you don't necessarily expect them to be connected. It's really cool. Okay. We've got a few more examples to go through, okay? Okay, and we're going through these examples because they do actually pop up later on in the series. So we're going to talk about now the dihedral group of, it's not order 6, it's order 12, but we label it with a 6 because it's based on symmetries of a hexagon. So if you have a regular hexagon, okay, sort of like that, you know, or you know, as close to that as possible, okay, then what forms of symmetry are there? Okay, well, your first thought might be well, all the reflections. So you've got that one reflection here, one here, one here, one here, okay, and yeah, okay. So you've got 6 reflections, okay, 1, 2, 3, 4, 5, and 6. Yeah, okay. So, and all of those, they have order 2. So as in, what the order of an element is it's the number of times that you have to multiply it by itself or add or whatever the operation is in your group, okay, to get back to the identity. So for a reflection, okay, you reflect it there, and then in the same plane or axis, you reflect it back, okay, so, and you end up where you started, so that's order 2. Okay, it's actually, it should say it's the minimum number of times, because you could do it 20 times, okay, a reflection 1, 2, 3, 4, 5, and so on, and you would get back to the identity, but it's more than it's needed. Okay, so we tend to say, so we go with the minimum. Okay, so those are 6 reflections. You also have 6 rotational symmetry. Okay, so you have the first one, okay, which I'm going to put in, is a rotation of 30 degrees, I think. Hold on. No, 60 degrees, sorry. Is it? I'm not sure. Well, hang on. Let's have a think, right? It's that. So yeah, that is 30. I was right the first time. Okay, so a rotation of 30 degrees. Okay, and we're going to stick with clockwise, okay, and they're all going to be clockwise. And the rotations that you there are, as I said, there are 6 rotations, okay, of order, not order, there are 6 rotations, so, no, hang on, it can't be 30 because then if it's 6 times 30 is 180, and so you'd only end up here if you do all 6, but you need to be able to do all 6 to get back to the identity. So it has to be 60. Good grief. Can you tell that I am smart? I am smart, you know. It's just I tend to think more in the abstract than the practical. Okay, that's the problem that I'm having here. Okay, let's carry on. So it's a rotation of 60 degrees. Okay, about the center. Okay, and there are 6 of those. Okay, now I'm not going to write all of those in. Okay, because what I can do, and I'm going to do this in green. Okay, is I can say, you know, I can say that we're going to have the first rotation R, okay, and that equals, actually, I'm going to write it up here. R equals rotation of 60 degrees, right? Okay, so that's the first one. Then R squared, okay, as in do R and then R again, would be a rotation of 120 degrees. R cubed, 180 degrees, and so on, until R to the 6 is a rotation of 360 degrees. And in fact, R6 is equal to 1, or the identity, because if you rotate something by 360 degrees, okay, or at least a 2-dimensional shape, and in this case it's a hexagon, okay, you end up back where you started. Okay, so you end up with 1, which we're labeling is this 1 is the identity here. Okay, okay, so R squared, R cubed, R to the 4, and R to the 5, okay, then it turns out that if you pair all of these with with one reflection and the same one all the way through, so we're going to go with reflecting in this vertical line here, okay, we're going to go with that reflection, okay, then you end up getting all of them, okay. Now, I'm not sure which order. You can work out what it is, which one refers to which yourselves, but what you end up with, okay, is a set like this, okay, and that, okay, is a group under multiplication, okay, which I'm actually going to call a dot here because sometimes we use x as a value, and you know, you don't want to get confused. But yeah, if you multiply any of those together, okay, you always get one of those. Now you might think, well, hang on, what about R to the 4 times R to the 5? Well, that's R to the 9. 9 isn't in there. But it comes back to this stuff I was saying about cyclic groups, okay? And if you think about it in a practical way, which I know I don't normally, I know I said that, but, you know, just go with it. In a practical way, you're rotating 9 times by 60 degrees, right? Okay, so what do you get? Well, you actually get a rotation. Well, you get a rotation of 180 degrees, which is r cubed, because you'll pass through 360, and we know that once you hit 360, that's the equivalent to 0 degrees, or a r to the 0, which is 1, the identity. Okay, and the same with the reflections. Now we also have the rule that that SR equals r to the 5s. Okay, and so if you've got s times r, okay, that means do a rotation of 60 degrees and then a reflection in the vertical line. Okay, because we set it by default as a right to left reading. Okay, then that is equivalent. That is the same as doing a rotation, a reflection in this, and then rotating by 65 times. Okay, so that's a rule. And if you follow these rules, okay, then you keep a group. Okay, you've got a group again. Okay, so that's another group, dihedral group, or symmetries on a hexagon. Okay, don't worry, this is the penultimate example. Okay, and this is permutation groups. Okay, so what is a permutation? Well, a permutation is, so suppose you take n numbers. So you've got 1, 2, 3, up to n. Okay, and that's a set. So you've got a set of n numbers, and this is ordered. This is very important. And I know ordered has come up before, and yeah, I know it can be a bit confusing. But order in this case just means that we care about what position each number is in, right? Okay. And if I want to permute these, so that just means change the order. Okay. So 1 might go to 3, 2 might go to 10, 3 would go, let's say 3 goes to 1. Okay, then we'll have something goes to some number k, and then n, actually no, we'll say n goes to some number k. Okay, all right, and that's a permutation. This is what's known as two-line permutation. You can actually also write these in cyclic form, what we call cyclic notation, and that just means that instead of writing 2 lines and all this sort of these arrows going between them, you just write in a line in brackets where different things go. So 1 goes to 3, so you start with 1, 1 goes to 3, 3 goes to 1, so you keep those in brackets. Okay, and then pardon me. So you keep those in brackets, okay, and and that's your permutation. Then next we go to 2. Well, we have 2 goes to 10, 10 goes to wherever, and that cycle ends or loops around again at 2, at something going back to 2. Okay, and then the same n goes to k, and that goes on for however long as well, right? And if you do the maths on this, on permutation groups, right, then you end up again with a group. Okay, and I think I did sort of say that, so I kind of gave it away, whatever. Okay, let's actually quickly go through an example of the example, okay, because that's not confusing. And let's just have a quick look at S4. Okay, so this is permutations of 4 elements, okay, which we're going to label 1, 2, 3, and 4, right? Okay. Okay, and let's look at the cycles 2, 4, 3, 1, and we want to, and let's say we're going to multiply that by the cycle 1, 3, 4. Okay, 2 stays as it is in that one. Okay, actually I should mention that if a number doesn't appear in the cycle or in anywhere along the line that you've written, it just means that that number is in a cycle of its own. It gets sent to itself. Okay, and we don't write it because why would you write something going to itself? It takes up space, time, and effort. Okay, and famously mathematicians are lazy. Okay, so how do we work this out? Well, the way it works is that, you go right to left again, okay, and what you're asking is, where do the numbers that I've sent through get sent to? Which, yeah, okay, so we start with 1, all right, read right to left, so we're sending in 1, 1 gets sent to 3, then 3 gets sent to 1. So 1, overall, 1 gets sent to 1. So that's in a cycle of its own. For the time being, we'll write it like this. Okay. Next, we have 2. 2 gets sent to itself in the first cycle, then gets sent to 4 in the second. Okay. Okay, so overall gets sent to 4. 4 gets sent to 1 in the first cycle. 1 gets sent to 2 in the second cycle. So overall, 4 gets sent to 2. So we can close that cycle off. And then finally, 3. Well, if it's S4, there are only 4 numbers in this sets that are possible to be permuted. So we know that 3 is going to have to be sent to itself, but let's go through the motions and double check that. 3 gets sent to 4 in the first one, and then 4 gets sent to 3 in the second. So yes, indeed, 3 goes to itself. Let's tidy this up and leave it as 2, 4. So if you multiply these 2 cycles together, okay, in this order, you get the cycle 2, 4. Okay. Final group that I want to cover, and this isn't one that's actually going to come up later. Okay, but I want to cover it because it is my favorite group. Yes, I have a favorite group. Okay, of course I do. Okay, and this is the Klein 4 group, sometimes known as V4. Okay, and it's my favorite group. Before I explain why it's my favorite, let's explain what it is. The rules are very simple. Okay, so the set V4, okay, is 1 and then 3 other elements. So 1 being 1 that we're used to working with, okay, an identity element, okay, and then A, B, and C are just 3 random things, okay, and we pair this again, in this case here, with multiplication, okay, and what are the rules? Well, other than the group rules, the axioms, okay, the rules are everything squares to 1. Okay, so that means 1 squared equals A squared equals B squared equals C squared equals 1. So all of them squared equal 1. Okay, and the product of any 2 non-identity element is the third non-identity element. All right. Now, what does that mean? Well, it means that if you've got A times B, that equals C. If you have B times C, then that equals A. And if you have A times C, that equals B. Okay, and then the same for the reverse. Now, the reason this is my favorite, okay, the reason this is my favorite group is that it pops up everywhere. Okay, I think actually in S4, okay, you can take a subgroup, which we'll come on to in a minute. Okay, and that subgroup is V4, which I think it's so cool. Okay, it just pops up everywhere. I love it. Okay. Okay, and what we can do with this one, okay, is, and I'll do it up here, is we can draw what we call a Cayley table. Okay. Okay, and this is basically a multiplication table. Okay, we call it a Cayley table because it's named after a mathematician called Arthur Cayley. He didn't invent them, he just popularized their use to depict groups. Okay, so let's quickly fill this in. Okay. Okay, and so yeah, you can see, so the Cayley tables are really good, really helpful because you're able to see the structure of the group quite quickly, I would say. Okay, and that's one of the reasons that we use them. But if you draw Cayley tables for other groups in other cases, sometimes you'll spot you'll spot straight away that they look like this or they look like something else, and you go, ah, that's the same group. Those are isomorphic. It's so cool. Okay, you can see hopefully how excited I am about V4. This is my favorite group. I love it. I really do. Okay, that's the last example. Hurrah. Okay, now I would like to quickly cover subgroups and subsets. So a subgroup, okay, as the name might suggest, is a smaller group contained within the larger group. Okay, and in this case, it just means it's a group in its own right. So it means that it's closed. Okay, this is the important thing. It's closed within itself. So if you take, for example, let's see if I can quickly find it, the integers mod 6. Okay, if you take C6 and you only look at 0 and 3, okay, well, 0 add 0 is 0, 0 add 3 is 3, 3 add 3 is 6, but 6 is 0. Okay, and they're the only possible answers that you can get from addition. So 0 and 3, okay, 0 mod 6 and 3 mod 6 also form a group, okay? And because 0 and 3 are contained in C6, it is a subgroup of C6. Okay, so that's a subgroup. That's what that is, very quickly. Okay. Now let's talk about generating sets. Okay, so what's a generating set? Well, I mean, again, the name suggests that it's something that generates, right? Generators, generating. Okay, so we will call this set S. Okay. And S has a bunch of elements, which let's label it as S sub 1, S sub 2, up to S sub k. Okay, and what this means is that if you take the product of any number of these elements of k, of these s's, okay, then you would end up getting the entire group. Okay, now if we look, okay, an example, a good example to look at for that is D6. Okay, if you take R and S, okay, so the rotation of 60 degrees and the reflection in the vertical axis, okay, and I know that this S and this S are sort of similar. Let's put a couple of lines here to signify that that's a capital S. Okay, then this set is a generating set of D6. If you follow these rules, okay, then you get the whole thing. Okay, and the reason that the reason I'm bringing this up is because it will relate to what we're going to be doing later on. Okay, worth pointing out, I would say that this is a minimum generating set. Okay, because you could add in r squared or r cubed times s as well. It's just, again, it's a bit redundant. Okay, because once you've got them, once you've got those, you don't, some of the times, you don't need to have extras. So usually when we talk about generating sets, we're talking about minimum generating sets. Okay, then if you decompose, is the word that we use, if you take an element, so actually let's take an element of D6. Okay, let's take r to the 4s. Okay, and if I were to write that as a product of generators, okay, and so by that I mean just as the generators on their own, basically get rid of the powers, right? Then that would be r times r times r times r times s. Okay, and when you do this, when you write it like an element out like this, okay, we refer to it as a word. Okay, and you can also do that for some other, combinations. So you could have R, S, S, R, R, S, R, S, let's say. Okay, and we could go through and we could simplify this. So, the S's here cancel out because they have order 2. So a reflection and then a reflection back is just itself. Yeah, not itself, is just the identity. It's 1, so we can get rid of those. Then you have r cubed, SRS. Okay. And hang on, I think I made a mistake here. Okay, yeah, it's not SR, it's... oh, no, it is. No, I haven't made a mistake. Okay, but what we can do, well, actually, let's look at this quickly, because this, okay, this implies that SRS equals r to the 5, because you multiply by s on the right hand side on both sides of the equal sign. Okay, it will cancel out with this one here, and you end up with SRS equals r to the 5. And what do we have here? We have an SRS. Okay, so we can change that. Oh, hold on, we can change SRS into r to the 5. So you end up with r cubed times r to the 5, which is r to the 8, which in D6 is the same as r squared, r to the 2. Let's try and make that look more like a 2. Yeah. Okay, so that's sort of the basics of group theory. Let's now head on and talk about reflection groups. Okay, and as the name would suggest, these are groups consisting entirely of reflections. Except it's not. Okay, a reflection group only has reflections as the generators. Okay, all the other elements could be whatever you like. Okay, by reflection we just mean order 2. Okay, you know, so an example. Okay, and rather than trying to be all abstract about this, let's talk about it through an example. Okay, so I'm going to draw out the tiling of the plane. Okay, so a complete flat plane, and I'm going to tile it with squares. All right, so what does that mean? Well, it means I'll speed this bit up, I think. Okay, so we've got our tiling of the plane with squares. Okay, so what reflections do we have for this? Okay, so by that I mean which reflections, which lines, okay, can you reflect this plane in entirely so that everything lines up, it stays the same. Okay, so the first one you might spot is vertical lines. Okay, if I reflect it this way, okay, in any vertical line of half length, okay, we're going to assume that these are unit squares, and I know that my drawing isn't perfect, but just go with it. Okay, and so these are going to be reflections in the vertical axes of half units. So we'll do those in dotted lines, and again I'll speed this bit up. Okay, so that's the vertical ones. Then you might have spotted that you can do the same in the horizontal lines. So let's put those in. Okay, and then finally, there is one more set of reflections, and these are the reflections in the corner-to-corner diagonals of all of these squares. Okay, so let's put those in. Okay, and then you also have the diagonals in the other direction. And that's a bit messy, I know. So I've made a digital one here that you can look at. Okay, and I'll quickly explain what some of the properties of this are, and also some of the sort of things words that we used referring to this. Okay, and that. So first of all, we have a cell. Okay, and a cell refers to any of the a cell refers to anything, basically anything on this, okay, that's in green or encapsulated by green. Okay, or I think it's black, or I think it's red on the image there. Sorry. Okay, so it could be any of the green lines or any of the small triangles. Okay, now the green lines are called walls. Okay, the lines of reflection. Okay, what are they walls of? They're walls of chambers. They are the small triangles. Okay, and you also get the support of the triangles, which refer to, so the support of the chamber, sorry, which refers to the three specific walls of that chamber, okay, that support it. So the way I picture it is it's some sort of physical manifestation that's been built, and the three walls there to stop it from collapsing. Okay, we also have a gallery. Okay, a gallery is often, and let's put, okay, the gallery is called gamma, okay, usually, okay, and a gallery is a collection of consecutive chambers, okay, so basically going from one point to another. So it might be, well, actually, I've done a couple, again, on a couple of images digitally over there, okay, which you can see. So you can see that gallery there, okay, and then it's also important to have a concept of distance in reflection groups. So that is the number of chambers required, the minimum number of chambers, sorry, required to go from one to the other. Okay, and the gallery can also have a length or a distance. Okay, so for example, I think the one in the, well, I'll put the length of the galleries of the ones that I've drawn digitally on the screen now as well. Okay, sometimes actually a gallery might stutter. Okay, and that means that it sort of goes back on itself. Okay, so it might go through a few chambers and then come backwards and go on in a different direction. Okay, that's a stutter because you don't need to go to those other ones. Again, it comes under this concept of redundancy. Okay, and then we have a couple more points to make. If you've got a reflection group, okay, which we will call W, okay, okay, and in this case your tiling has chambers C in the set of chambers which we label as sigma, okay, then you can have an action on those chambers, and that just means a way of doing something to them, okay, that using the reflection group, okay, so it might be, so if W is an element in big W, okay, then we label WC, okay, as W acting on the chamber. So what does that mean? What that means is that suppose you are at some chamber C, okay, and W is an element of this reflection group, so it takes a number of these lines, okay, and you go through those reflections, you end up in a new chamber, which we will call C prime, okay, and that just means that, so W refers to the reflections you go through, okay, and C prime is whatever new thing you end up with, okay. So we say that that W is, the action of W on sigma is transitive, Okay, if for all C and C prime in sigma, there, oh, and I think that's gonna get, yeah, that's gonna get covered up. So there, I don't know why I'm moving my head, because it's in a, my head is in a box here. That's not moving, so I don't know why I am. Okay, there is W in big W, okay, with C prime equals WC. So basically, no matter what chamber you're in, you can always get to some other chamber, okay? If this action, okay, if the action of W on sigma is free, okay, so that means that the stabilizer of the action is trivial, so it's just it's just one. Okay, if you're unfamiliar with stabilizers and actions and all this, I will put a link to the Wikipedia article on them. It's fairly easy to understand, I think. Okay, it should only take you. It shouldn't take too long. I might do a bonus video if I can be bothered. Okay, but we say that it's free if the stabilizer is trivial, and if that action is free and transitive, all right, then we say the action is simply transitive. Okay. Okay. So that's reflection groups. Okay. I should mention that we name this reflection group. Okay, this W is named known by 442. Okay, because 442 is the order of the pairwise reflections. No matter which ones you choose, the order will always be either 4 or 2. Okay, yeah, okay, and there are a bunch of sort of, theorems and propositions and lemmas and whatever about reflection groups, but they're long, confusing, and I can't be bothered to, and they're a bit beyond the scope of this series. Okay, but one that I do want to mention is theorem 1.1 of my master's project, which I've put here. Okay, and that says, so suppose that you have a finite reflection group W, and that acts on a set of chambers sigma, and the H is W invariant. Okay, and that just means that no matter what hyperplane you choose, so no matter which reflection line you choose, okay, if you go through a series of reflections, it's still in this set of hyperplanes of this reflection group. Again, it's closed. You don't end up with something weird. Okay, then, and the reflections in those hyperplanes, in those reflection lines, generate all of W. So if you take all of them and you combine them together, then you get W. Okay, then we have, firstly, the action of W on sigma is simply transitive, and the size of the set of chambers sigma is equal to the size of the reflection group W. The second point is that if C is any fixed chamber, then the reflections in the walls of C generate W. And thirdly, H, which refers to the set of hyperplanes, okay, then it contains all hyperplanes in this reflection group, okay, with SH and W. So basically, okay, it sounds confusing, and it sort of is, but the TLDR of it, okay, is that it allows you to equivocate the reflection group to the set of chambers and shows that the generator set is not dependent on any one chamber. No matter which one you choose, you will always be able to generate the whole group, which I think is, I think it's really cool. The proof is fairly long. I think it took me 2 or 3 pages in my project, okay, which is actually linked in the description below. So if you want to have a look at that, or at any of the other things that I didn't mention in this video, then by all means, you can see that down there. And that's the end of this video. I hope you enjoyed it. Okay, keep an eye out for the others in the series, and I'll catch you in the next one.